Hi everyone, it's Sorkin. Today we have a problem when we are given a root of a binary tree and each node of a binary tree should have one coin. But the given binary tree has the nodes either have excess or they have deficit of the coins. So for example, in this case, the root has 3 coins and the left and right child has 0 coins. And we need to return the minimum number of moves required to make every node have exactly one coin. So for example, in this case, the root has 3 coins. And if we are distributing one to left, one to right, so every node has one coin now, and we are making 2 moves. So for example, let's say we have another example. We have here 0, we have here 3 coins, and we have here also 0 coins, right? In this case, we need to, how many moves we need to make? We need to one move here and one move here, so 2 moves, plus one move that this is for the right child, right? And another one is for so one is here, we moved one here, right? And we moved one coin here, so totally we are making 3 moves. Let's take one more example. For example, let's say in this case, we have this binary tree where we have excess coins here. We have excess coins here, and we need to move these coins to here 0, 0, and 0, right? So how many minimum moves that we need to make? So let's just count them. So we are going to make from here 1, 2, 3, 4, 5, 6, right? We are going to make 6 moves. The same, we are going to move one coin from here to here, right? This path. And the same way we are going to move another coin here, which is plus 6 moves. And also we are going to move one coin from here, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and the 6. So we are going to one move here again, 6, right? So totally we need to make 16 minimum moves in order to each node has equal number of the coins. So which approach we're going to use here? As you can see here, for example, in this case, right? So we have here how many excess coins? We have here 2 excess coins. What it means? It means that whatever the scenario is, we are going to move those 2 excess coins to the upper one, right? So to the upper node. So which means that we are going to move one coin from here. So one coin we will leave here because we need one coin for this node, and we will move 2 excess nodes to our root. So these nodes will be moved, right? So how about here? Here we have one node, we don't need to. So we have 2 excess nodes, right? Again, we are calculating that how many nodes we need to. So we have already here one node, right? We are going to move these 2 nodes to our root node, right? To here. How about this one? Let's go to the left node. Let's go to the right node, right? So here we have 1 excess nodes, one we are leaving here and one we are moving, right? One we are moving, this node has one coin, so we are not doing anything here. So we are moving 1, right? 1 excess coin. So 2 plus 1, we have 3 coins, right? So equals to 3 coins, which means that the 3 coins we need to move. So they are excess coins we need to move. How about this one? In this case, we have 1 deficit coin, right? 1 deficit coin here and 1 deficit coin here. So whatever the scenario is, we need to move 2 coins to these nodes, right? To these nodes. So which means that we have to move 2 coins from here. So how about here? So here we have 1 coin, we have 0, we need to move 1 coin here. So right, and we need to so how about our root? We need to move 1 coin to our root and from our root to our left child, right? So 2 plus 1, we need to also move 3 coins here. So what it means? It means that we need to move, in this case, we need to make 2 moves. We need to make 2 moves. We need to make 1 moves here, 1 move from here, 3 moves from here, and 3 moves to this coin, right? To this node. And these 3 nodes, we are going to distribute 2 here and 1 here. And we are going to distribute to these coins, to one here, one to here. So it means that if we are going to calculate all these excess and deficit for each node, right? If we are going to DFS our binary tree, and for each one we are going to calculate that either deficit or excess absolute value, that will give us the result. So for example, let's calculate this one. How many? 2 plus 1, right? 2 plus 1, 3. 3 plus 3, 6. 6 plus 3, 9, right? 9 for the left subtree, right? For the left subtree we need 9. How about for the right? So we are moving 3 from here for our excess, right? 2 here. So 3 plus 2 plus 1, 6, and the plus 1 plus 1, 1 plus 1 gives us 9. So also here 9, right? So here we also need 9 and 9 here. 9 plus 9 gives us 18. Okay, first thing, let's create our result that we are going to return, and we will add to our result. Let's create our DFS function that we are going to calculate the excess and the deficit coins in our left and the right subtrees and add that to our result. Let's pass our root here, and let's return our result. And let's now implement our DFS function. Our DFS function, it's gonna return int, right? Our excess and deficit coins. DFS, we are passing our tree node here. Let's just call it a node, right? And what we are gonna do, first let's just check the base case if our node is equals to null, right? So in that case we are going to return 0. Okay, and now let's calculate the excess or deficit nodes in the left and the right subtrees. So let's do first for the left. So what we are going to do, we are going to DFS, we are going to recursively call our function left, and the same exactly we can do for the right. And so now we have calculated excess or deficit coins on the left and right subtree. Now we are going to add to our result, right? We are adding to our result. We are taking the absolute value. Doesn't matter, we need to move to the node or move from the node, right? So we need to make that move. Absolute value of the left and absolute value plus absolute value of right. Okay, and the next thing is we are just so we have calculated that. Now we are returning that for that node, right? We are returning that the excess coins for that node. So node value plus left plus right, and also we are taking one coin that we are going to, because the one coin we should keep for the node itself. And that's it. Let's run it. Okay, DFS. Alright, great, it works as expected. Let's calculate the time and space complexity. What's the time complexity? Time complexity in this case, we are visiting each node. It's of n, and the space complexity is determined by the number of recursive calls. In the worst case, it's going to be also of n. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.